Assalamualaikum and greetings to all. We are from Expert TV and today we're going to explain about the sizing and costing for absorption column. For the first part, we're going to explain the sizing of absorber consists of diameter, height and thickness.
Hi everyone, today I will walk you through the formulas of used to calculate the diameter of absorption towers, especially focusing on the tray tower and also the pipe towers. This is crucial in designing efficient gas absorption system. So for tray towers, the diameter is typically determined to use to prevent floatings and ensure the efficient vapor-liquid contact. And here shows the formulas to determine the tower inside diameter dt, which obtained from the center textbook equation 30.11. And the steps to calculate dimension are shown as follows. So first, we need to calculate the flow ratio parameter FLG. The flow ratio parameter relates the liquid and vapor flow rates and their density. The formula for calculating the flow ratio parameter is shown in step 2, where L equals the liquid mass flow rate, V equals vapor mass flow rate, rho L equals liquid density, and rho V equals the vapor density. And the formula below shows the ratio of tile corner area and the tower inside cross-sectional area, and their relationship with the flow ratio parameter. And next, we'll use the value of flow ratio parameter calculate in step 2 and based on the type of tray used such as sieve, WAF, and bubble cap trays to give us a capacity factor denoted as CSB using the floating correlations chart which can be found from the Cedar textbook figure 30.4. And in this step, we will determine the floating capacity parameter C, which is crucial in estimating the floating velocity. The formula for calculating the capacity parameter is shown as on step 4, and where each term represents a correlation factor for different operating and physical conditions. So let me explain each component, where Fs is the forming factors. So for non-forming system like distillation, the Fs equals 1. And forming system like absorption with heavy oil equals to the range of 0.5 to 0.75. And FHA stands for the whole area factor where the value of a bubble caps and valve will be 1 and while also 1 for the sieve tray with the ratios of tile corner area and tower inside cross-sectional area more than 0.10. And SST is equal to surface tension correlations factors can be calculated using the following formulas. And once all these factors are calculated, they are used to calculate to get the value of capacity factor C. After obtaining the capacity parameter from step 4, we can calculate the floating velocity of the vapor using the formula on step 5. And lastly, we got all the parameter values required for the calculating of the diameter of the tower. We substitute it into this formula, and this gives us the internal diameter of the tray tower in feet.
Now let's look at how to calculate the height of a tray tower, which we will denote as L. We will be using this formula where L is equals to n actual minus 1 times the tray spacing plus height of sum below bottom tray plus the disengagement height above top tray and the feed tray spacing and as well as the skirt. Note that the n actual is the actual number of trays, where the value for n actual, height of sum below bottom tray, disengagement above top tray, feed tray spacing, and skirt can be obtained from the Aspen Plus or by assumption.
Now let's look at how to calculate the thickness of tray tower. To find the minimum wall thickness, which is also known as TP, first we need to assume the value for well efficiency, which is E, either 0.85 or 1.0, and then from given equation where PD stands for design pressure, I stands for tower internal diameter, and S stands for maximum allowable stress, we can find the minimum wall thickness. To calculate thickness to withstand wind load kW for vertical tower, firstly, we need to find out outer diameter using the equation dO is equal to Tp plus Di. To find the Tw, we can use the given equation where the L is equation stands for height of tower. Next, to calculate shell thickness Ts, firstly we need to calculate the average vessel wall thickness Td by summing the minimum wall thickness Tp and the thickness to withstand the wind load Tw. Even for non-corrosive condition, a corrosion allowance Tc of 1/8 inch should be added. And the equation to calculate shell thickness is average vessel wall thickness plus corrosion allowance. Next, we need round up to the next increment and finally choose the inclusive and sum the value with the calculated final shell thickness, which is TS.
So let's try an example scenario. This is a reboiler absorber operating as an eternizer at 400 PSI to separate light hydrocarbon feed. Conditions at the bottom tray are shown as below. And if sieve trays are used with hole area of 10% and a 24 inches tray spacing, determine the tower diameter. Assume that 80% of flooding and a foaming factor of 0.75. So let us start with extract the required data and insert into the green color cell. Then next we have to calculate the surface tension, glow ratio parameter, and next we have to select the foaming factor. So according to the questions, it is a foaming system with a foaming factor of 0.75. Then we have to select the 80 per 80, and since the FLG is greater than 0.1, we are choosing this, and we will get 80 per 80 for 0.2. Then next we have to select the whole area factor FHA. So in this scenario, the sieve tray is with AH per AA greater than 0.1, and therefore the FHA is equal to 1. Then we calculate the capacitor parameter C, and the tray spacing and also is given in the questions, which is 24 inches, and based on the figure 13.4 we found that the CSB is 0.1 feet per second. The C value is calculated automatically and also same as the flooding velocity. Then lastly, we assuming the for flooding factor by the questions given 0.8, then the tower internal diameter is automatically calculated, which is 4.9891 feet.
And we're moving on to the next part for the pack tower diameter calculations. For pack tower, we also use a similar approach but different correlations. The aim is again to avoid floating and also ensure proper contact. And here shows the formula to determine the tower inside diameter dt, which obtained from the Seidel textbook equation 30.14. So first we're going to use the level floating correlations, equal factor, vapor, and liquid flow rate, density, and packing factor. Y is the floating velocity factor with a range of 0.01 to 10. Fp is the packing factor, refer to the table 13.1. And G is the gravitational force. F is a fraction of floating velocity equal to 0.7. Rho G is the density of gas. Rho L is the density for liquid. And F rho L is the density ratio in the range of 0.65 to 1.4. And F mu L is a liquid viscosity in the range of 0.3 to 20. And next, we're going to calculate the flow ratio parameter FLG and the flow ratio parameter, which is same as a tray tower. And formula 30.17 and fitting 18 shows the formula for the parameter required for the level floating correlation in step 2. Next is the packing factor table 30.1. Here we refer to table 30.1, which given us the packing factor based on the type and size of packing used. The common example include racing ring, power rings, elbow settles, and this factor is needed to find the floating velocity. Moving on to the last step, we're going to use the level correlations and packing factor to calculate the floating velocity UF. After calculating the floating velocity, we're going to use the same equation in step 1 to calculate the diameter of the pack tower. And this given the internal diameter of the pack tower in feet. And so in summary, both tray and pack tower are relying on avoiding the floating. So we can calculate a flow ratio parameter, finding the floating velocity, and finally use that to find the diameter. And the main difference lies in the type of floating correlation used, which is graph based for the tray and level based for the factor.
Next, let's go over how to calculate the height of a pack tower, which is denoted as L. And let's say our packing diameter, which is denoted as dp, is 361.6 mm. Then we will first require a parameter known as HETP, or height equivalent to a theoretical plate. This value depends on the packing type and process conditions. And this table helps us to choose the appropriate HTTP value based on different conditions. So for example, for random packings with low viscosity liquids, the HTTP is taken as 1.5 times the packing diameter, which is dP, where the calculated HTTP value would be 542.4. Once we have the HTTP, we will be using equation 13.9, where we will multiply it by the theoretical number of trays denoted as an equilibrium to get the packed height.
Now look to calculate the thickness of packed tower. To find the minimum wall thickness, which is also known as TP, first we need to assume the value of the well efficiency E either 0.85 or 1.0. Then given the equation where the PD stands for the design pressure, the I stands for the tower internal diameter and S stands for the maximum allowable stress, we can find the minimum wall thickness. To calculate the thickness to withstand the wind load, Tw for vertical tower, firstly we need to find out the outer diameter. Using the equation dO is equal to Tp plus Di, the Tw we can use the given equation where the L is equation stands for the height of tower. Next, to calculate the shell thickness Ts of the packed tower, firstly we need to add a corrosion allowance Tc of 1 over 8 inch. Then, calculate the average vessel wall thickness Tv by summing the minimum wall thickness Tp and the thickness to withstand the wind load Tw. Substitute the calculate value Tv into the formula where the shell thickness is average vessel wall thickness plus corrosion allowance. Next, we need to round up the next increment and finally choose the inclusive and sum the value with calculated final shell thickness Ts.
Now let us try an example scenario. Water is to be used to absorb acetone from a dilute mixture with air in a tower packed with 3.5 inches metal pour rings. Average conditions in the tower are 25 degrees Celsius, 110 kilopascal. In liquid phase, its density is 62.4 pound per cubic feet and a flow rate of 77,270 pound per hour, and also 75 dyne per cm of surface tension and 0.92 cp of viscosity. In vapor phase, it has a density of 0.0803 pound per cubic feet and also a flow rate of 44,540 pound per hour. So to determine the column diameter for operation at 70% of flooding, first and foremost, we have to extract the required data. Then we calculate the glow ratio parameter and the y value, the density function, and the viscosity function. And lastly, we have to calculate the flooding velocity. So we are using the information given in the questions and referring to this table 13.1 packing factors for calculating flooding velocity, and we found that the packing factor is 16, and then we input in this green cell and we will calculate the flooding velocity. Then next, the tower inside diameter will be calculated automatically and we get that it is 4.3088 feet.
Okay, the next one we will be discuss the cost estimations involved in Absorber. So the main focus here is to understand the calculations and formula required for accurate costing of pressure vessels, pack and also tray, which are very critical component in chemical industry. So the next one, let's start with the formula used to calculate the purchase cost of pressure vessels, denoted by CP. The formula is as follows: CP equal to FM CV plus CPL. So CP itself represents the purchase cost of the pressure vessels. FM is the material of construction factor. Depending on the material used, CV is the cost of the empty vessel, which included the nozzle, manhole, and also support. CPL represent the added cost, including platform and ladders, which depends on the vessel size and design. So the best CE index is given as 567, which is a very important reference for these cost calculations. So this formula help to estimate the cost for different size and configuration of pressure vessels. Okay, for the next one is the material of construction represented by FM. The material factor is to determine the cost as is varies based on the material chosen. So here is a table showing different materials and their factor. For example, like carbon steel has a factor of 1, which is the baseline. So the choice of material will directly impact the overall cost of the pressure vessel, and selecting the material is very important for the cost and performance. Okay, the next one, the costing of empty vessel, denoted as CV. The cost is determined based on the weight of the vessel and its design type. So whether it horizontal or vertical, the equation are as follows. For the horizontal vessels, when the weight is between 1,000 and 900 to 20,000, the formula is given as follow. And same goes with the vertical vessels with weight between 4,200 and 1 million. The formula is given as follow in the table. So these equations allows us to estimate the cost based on the weight of the vessels and their orientation. So the next one is the additional cost related to platform and ladders represented by CPL. The cost depends on the diameter and length of the vessels. So the equation for both horizontal and vertical vessel uh, are as follow. So for the horizontal vessel with diameter between 3 and 12, the CPL itself is 2275, diameter the power of 0.2094. And the next one for the vertical vessel with diameter 3 between 3 and 31, and the length is between 12 and 14. So the CPL itself is calculated using this formula, which is 410, diameter the power of 0.73960, and the length the power of 0.70684. So this cost is added to make the maintenance platforms, ladder, and other equipment are included, which are very important for the larger vessels. Okay, now let's talk about the tower, which are another form of pressure vessels. The cost is calculated similarly, but with the slightly different approach for the both empty vessel cost and added cost. For tower with weight between 9,000 and 2.5 million, the cost formula are given as follows. So again, these costs are critical for make the tower structure is functional and also for the operation and maintenance. So now let's look at the base FOB purchase cost for pressure vessel and tower. So which is the price before any additional costs are added. So the graph here shows how the cost scale with the size factor and weight. As you can see here, larger vessels tend to have higher purchase costs, and the type of vessel, horizontal or vertical, also influence the cost. So this provide a clear visual representations of how the size and design impact pricing in the industry.
Now I will be explain about how we're going to estimate the cost of pack tower. So the packing inside the tower help with the mass transfer between the fluids. And this packing come in two types. The first one is the dump or render packing, and the second one is the structure packing. The formula shown here is the purchase cost of pack tower. FMCV plus CPL is the empty vessel, which had been explained by my teammates in previous slide, and the VP, CPK plus CDR is the packing parts. VP is the volume of the packing in the cubic feet, and CPK is the install cost of the packing in dollars per cubic foot, while CDR is the install cost of high performance liquid distributor. As I mentioned earlier, there are two types of packing tower. The first one is dump or random packings, which are more cheaper and come in various materials like metal, plastic, and ceramic. And their cost data is available from vendor reference in table 16.19 in page 440 in SADA textbook for addition. And the second types of packing of tower is structure packing, which are actually more efficient because they allow better separation, lower pressure drop, and higher capacity. But they are more expensive and mostly made from stainless steel. And if there are no vendor quotes available, we can use estimated install cost of $285 per cubic foot for structure packing. And finally, for liquid distributor, which are important for even fluid flow, the rough install cost is $140 per square foot of column area. And the redistributor are recommended every 20 feet of packing height for optimal performance. The table 16.27 here is for the install cost of dump packings, which are actually developed by taking the average of those costs indexed to CE equals to 567 and adding some additional values from vendor, include cost for 6 different dump packing and 5 different material.
Okay, now I will calculate the pack column costing for the Excel, which before this we need to identify the weight, diameter, and the height of the pack column tower. So firstly, we calculate the purchase cost, which if it is under this range, we can logarithm the weight it become these equations, and then substitute inside this equation, we get the CV. Well, next was calculate the cost CPL, which if the diameter and the length is under this area, which means we can proceed to calculate the CPL, which substitute this equation inside it and then get the answer. Well, for the next one was we assume it is carbon steel, so from table 16.26, the material factors will be the one, and let's substitute the equation it here, so we will get the CP. Well, next one was volume of packing VP, which the R we get from here we by divide 2, the diameter divide 2, and then the height, and then 3.14 multiply with R square times with the H. So next one was estimate installation cost CPK. So this is based on the 16.27 table. We get $50 per 50 cube. This is just the assumptions. While total installation costs, since it is absence of vendor quote, assume install should be 140 ringgit. I means the ringgit per feet square area. So the CTR will be the 3.14 multiplied with the radius square times with this. So we can get the answer CDR. While the last one was total pack column. So because of based on the table 16.26, we get the FM equals to 2.1. While multiply and sum it together, this CP value, we can get the answer here.
Next, I'm gonna be talking about the costing for plate or tray tower absorption. So first, we have the formula for CP, which is the FOB purchase cost, which is for carbon steel construction and includes an allowance for platform, ladders, and nominal numbers of nozzles and manholes, where it given by CP equals to FM CV plus CPL. For the costing for plate and tray tower, we should add CT, which is the cost of the installed trays, which given by CT equals to NT, FNT, FTT, FTM, and CBT, which CT is purchase cost of tray tower, NT is number of trays, FNT is factor number of trays, FTT is factor of type of trays, and FTM is factor of type of materials, and CBT is the base cost. For the FNT, which is the factor of number of trays, we can follow the formula in the textbooks, which is 16.168, where FNT equals to 2.25 over 1.0414 to the power of NT. So, if the number of tray is bigger than 20, the FNT will equals to 1. And if the number of tray is below than 20, FNT is greater than 1. So for the FTT, which is the factor of type of tray, we can see the tray type and the factor of type of tray below, where the sieve where FTT is 1, valve FTT is 1.18, and the bubble cap 1.87 for the FTT. Next is the factor of type of material, FTM. FTM depends on column diameter in feet, where we can see below. For carbon steel, the FTM is equals to 1, and 303 stainless steel, the FTM is equals to 1.189 plus 0.0577 times inner diameter. We can look at another one where 316 stainless steel, the FTM is equals to 1.401 plus 0.0724 times inner diameter. So for the base cost, CBT, CBT is for the shift trace at the CE cost index of 567, where the inside diameter of the tower is in feet and the equation is valid for 2 to 16 feet. You can find this equation in our textbook where it is equation 16.67.
Okay, now I will calculate the tray tower costing for absorption column. So we need to extract the informations, which is the weight, diameter, and the height tower. First calculate the purchase vertical tower, which is, if it is under the range here, we can logarithm it. Well, after that, we substitute inside these equations, we get the CV. So next is calculate the cost, CPL, platform, and ladder, which, if the diameter and the height is under this range, so you can calculate the CPL by substitute both of the equation inside here. Okay, next, while step 3 was purchase cost of tower CP. So from here, we assume as it is standard steel. So in this table, we will identify that material factor for carbon steel is 1. So substitute the CV and the CPL, we get the CP. Next is calculate the best cost. So which is substitute the diameter, we can get the CBT. So next, we determine the factor FNT, FTT, and FTM, which we assume as 50. So as it's less than 20, we can assume this formula. So we can calculate the FNT. While sieve tray is chosen because it is simple in construction, low entry, and so on, blah, blah, blah. So FTT will be the one. And then the material of constructions are from here, we assume as stainless steel 304. So it is 1.7. So the next one, we calculate the cost by multiply the NT, FNT, FTT, FTM, and CVT together it. So we will be the value for CT. So after that, lastly, we calculate the bare costs for CBM, which from table 16.11, we identify that FBM was 4.16 for vertical pressure vessels, and then the L and the pounds was 797.6, while the 600, which it is identified from this table. So substitute it inside these equations, we will get the CBM. So the total cost will be CBT, if not mistaken, is CT uh plus with the C CT times with 4.4, which is Ringgit Malaysia conversions.
Hello, I'm Anderson and I'll talk about the general construction. First, for the shell material selection. Typically in the industry, the shell of the exhaustion column is constructed with carbon steel and stainless steel. The second is about the mounting. Typically, it is vertically mounted. This is because we want to have the liquid and gas to be in contact as much as possible. Third is about the support plate design. The design of bed packing should have at least 75% of free area for passage of gas to offer as low resistance as possible. Fourth, about the packing support. The simplest support is a grid with relatively widely spaced bars on which a few layers of large restrict or partition rings are stacked. Now let's talk about the distributors. For the distributors, they have two types of distributors, which is liquid distributors and gas distributors, and here we have few examples of them. For the trough type distributor, it consists of long channel trough fed by a parting box, ensuring even liquid distribution over the packing. It's ideal for handling very high liquid loads and suitable for column diameters of 900 mm and above. For the spray nozzle distributor, it employs spray nozzle to disperse liquid as fine droplets over the packing surface. It is ideal for low liquid flow rates and large diameter columns but prone to clogging. For the perforated plate distributor, the uniform holes of the perforated plate allows the uniform distribution of gas across the column. It is simple and cost-effective design and works well in small and large diameter of columns, but can risk flooding if gas flow rate is too high. Now let's talk about the gas injection plate. It is used to inject gas into a system at a specific point. The focus was to inject the gas in a localized manner. It is not designed for uniform distribution, but for target injection of gas to promote mixing in liquid phase. It is often found in operation where local high concentration of gas is needed.
My name is Satish Reddy Vain, and now I'm going to explain about the packing inside the absorption tower. Actually, packing in an absorption column plays a crucial role in enhancing the contact between the gas and liquids. It refers the structure or random material like ring, saddles, or especially design shape fill inside the column. So the main purpose of the packing is to increase the surface area available for the mass transfer without significantly increasing the pressure drop. When gas rises and liquid flows downwards to the packing, the increased surface contacts improve the absorption efficiency. So this allows the target gas component to be effectively absorbed into the liquid phase. And this is a critical processes like gas purification, scrubbing, also for chemical absorption. We know that absorption towers are widely used in gas purification, air pollution control, and chemical processing, offering a reliable and continuous method for selective removal of gas component. So let's see how does a absorption tower works. So in a typical setup, gas enters from the bottom of the tower and flow upward, while a liquid solvent is introduced from the top and flow downward. So this creates a counter current flow, maximizing contact time and absorption efficiency. As the gas rises, the target component like carbon dioxide, sulfur dioxide is absorbed by the liquid. So inside the tower, there may be packing materials or trays that helps increasing surface area, improving interaction between the phases. The clean or stripped gas exists from the top while the rich liquid, now containing the absorbed component, is collected at the bottom for the further processing or regeneration. This is an example of equipment specification sheet of an absorption tower. So this sheet outlines the design and operational parameters for those absorption towers. So from here we can know that how the system is designed, the temperature range, and also the pressure range of the absorption tower works. So we can also know that the volume of each column that contains molecular sieves packed to a certain height. Also can know the bulk density of the absorbent and also the key parameters like bed voltage and pressure drop of the specified performance evaluation. So the construction section details materials such as SA 516 GR70 for the shell and heads and also SA 105 for flanks. So the columns are equipped with manways, lifting lugs, and also nozzle arrangement for inlet and also outlet instruments. So this sheet serves as a technical blueprint for engineering, procurement, and also for the operation of the purification, ensuring the safety, efficiency, and also the regulatory compliance of the absorption tower.